today face an almost impossible workload, constant innovations in research, calls, emergencies, and back-to-back patients. Providers need help. Meet PharMe. PharMe is not a replacement for your doctor, but a partner, keeping them informed with the latest treatments, drug updates, so they can focus on what they do best, caring for patients.
Hello, I'm Berk Yılmaz, Master of Science and Electrical Engineering student at Columbia University.
Hi, I'm Ishaq Khan. I'm a master's in data science student here at Columbia.
And my name's Dan Harvey. I'm a Master of Science in Computer Science Machine Learning here at Columbia University. And when was the last time you saw your primary care provider without waiting weeks or even months for an appointment? Doctors are so overwhelmed, endless patients, and mountains of reporting. In 2024, there were 44 novel drugs introduced and over 10,000 updates. By the time they get home, do you really think they have time to go over the latest FDA drug approvals or pore over clinical notes? Doctors are humans too. They need time to spend with their family, or maybe even decompressing with Netflix. But PharMe is not human. It's AI. Introducing PharMe, a cutting-edge tool powered by a specialized large language model. PharMe is fine-tuned with regular updates from the FDA Drug and Product Database. This means it's always containing the latest information on drugs, biosimilars, and other critical updates, right at your doctor's fingertips. PharMe is not replacing your doctor, but empowering them. Healthcare providers can focus on what they do best, caring for you while staying up to date with the most advanced medical treatments available.
So how does PharMe actually work? This is an overview of our system, which incorporates different technologies that we've reviewed in class. We begin with an initial data collection and fine-tuning process that parses the FDA database for a preset amount of data. For this initial project, we decided to scrape all of 2024 data. Then we configure an Apache Airflow where we have a monthly scheduled workflow to pull in data from the FDA on a regular basis. This data is then used to fine-tune the pre-trained LLM available on Hugging Face, a process that we reviewed during assignment number 4. With this fine-tuned LLM, it's then possible to provide symptoms and diagnoses in order to generate a list of medications that should include any applicable biosimilars. To go a bit more in detail on the actual data sources, the first is a Mimic3 clinical database, a large, freely available database comprised of health data from over 40,000 ICU patients between 2001 and 2012. This data is used to train the clinical Llama 3 8 billion parameter LLM released by Meta. For actual fine-tuning, like Dan mentioned, we incorporate regular updates from the FDA's Purple Book, a list of FDA-licensed biological products, including biosimilars and their reference products. These updates are released in monthly CSVs extracted by our Airflow pipeline. And just to revisit why a project like this is even necessary in the first place with actual data, here you can see on the left for 2024, the number of updates to approved drugs fluctuating month to month, increasing the difficulty for providers to stay on top of. And on the right, the total number of approved drugs grows and is on track to grow more rapidly given the implementation of AI in the drug discovery process. Diving deeper into our actual system, here's an overview of our Airflow DAG. We start by getting the most current data if it's available, merging it into the currently stored data from Google Cloud, and then running our fine-tuning pipeline.
Evaluation was an important aspect of our project. We saw that our model, Medical Llama 3, with 8 billion parameters, provided better precision, recall, and F1 score compared to other models. Our model was pre-trained on a total of 3 datasets and approximately 250 patient-doctor dialogues for context. The first example we wanted to show was a common disease, asthma, and how our model responded to it. By predicting a total of 12 medications, it even exceeded our prediction rates. But as we know, asthma is a disease that many people have. For example, I have been undergoing asthma treatment for 5 years and have been taking some of the medications mentioned here. To challenge our model further, we decided to select and test with more uncommon diseases, such as Hashimoto's thyroiditis. It's not a disease seen in many people. We want to expect that the precision of the model answers to decrease. However, contrary to our expectations, we achieved 100% accuracy in the results. We want to show attention patterns across layers and heads of the model. In early layers, like layer 0, focus on local patterns, linking nearby words like a and high. These layers capture low-level synthetic relationship, helping the model understand the structure. Deep layers, such as 31, shift to global patterns. Here, attention has to identify connections between words like high and headache, which are crucial for understanding semantics and the context. Each attention head plays a specialized role, as shown by the color-coded grid. Some heads handle positional dependencies, while others capture abstract concepts like meaning or relationship across the sequence. What this tells us that the transformers are hierarchically processing data, starting from the basis and gradually building deeper, more meaningful representations. Actually, this ability to focus on both local and global context is why these models are so effective for tasks like summarization, sentiment analysis, and translation. To visually demonstrate how our LLM model worked, we created a model that provides the prediction counts of tokens for the questions we asked as a chart bar. This visualization demonstrates how attention patterns in a transformer model contribute to generating meaningful predictions for a given input query. For example, for the input, list of medications for high fever is processed using a tokenizer and passed into the model. The top predictions show the probabilities for the words the model believes could follow the input context, such as and, patients, or treatment. These predictions reflect the model's understanding for the query, guided by the relationship it identifies between words. Then we wanted to choose an automated way to fine-tune our LLM model, because we had to pull data via an API from the FDA and use it for fine-tuning for our model. First, we wrote the code we wrote. We created an algorithm that automatically retrieves data from APIs for the selected data ranges. But when we first get the API, data set was messy. So we fine-tune our model with two functions that automatically transform this data for use for fine-tuning. For subsequent fine-tuning process, we decided to carry them out systematically with the help of Apache.
When you start up PharMe, the first thing you see is when the system was last trained, keeping you reassured it's always up to date. Your doctor just gave you a diagnosis. They type in the main condition into the primary field. They can also add any additional details or relevant information in the secondary field, such as other conditions. Once everything is entered, PharMe goes into inference mode, processing the prompt. In moments, PharMe represents a tailored selection of drugs, biosimilars, and treatment options for your doctor to choose from. It's fast, efficient, and designed to empower your healthcare provider with the most current options available. That's PharMe, bringing precision and speed to your care. Thank you.